Welcome back to Cloud Computing and Big Data. We have our second part of our practical lecture 11.1, using data mining and also recommendation techniques in the cloud. So part one was really a little bit about data mining in the sense of using association rule mining, which is, let's say, a term that is quite known in data mining and is basically something what you already know a little bit from the shopping list. You have heard probably that people can analyze your shopping behavior, and there were two algorithms in the first part we looked at. One was the a priori algorithm and the other one the FP growth algorithm. And of course, all is based on lecture 11, which established the idea how these algorithms work and why basically the tree-based approach of FP growth has a better performance than, for instance, a priori. And also in the sense of scaling for big data, what this course is about, you have to think about that the tree-based approach is a way to go. So, however, looking back on the association rule mining, you have also seen we purely looked at transactions, right? We looked at how basically people have shopped, what they put in their basket, what they paid for. There was not something like an necessarily ID of a user. There was no idea about this. And this will now change when we talk a little bit about recommendation systems, just to give you an essence that also this can be nicely done in the cloud. Algorithms are implemented in different packages. We use here now the surprise package in the second part. But as you don't know much about the recommendation techniques, we still have to establish this a little bit with some theoretical meaning, but then also go quickly in the practicals, as this is a practical lecture. Again, for you as a reminder, some people would say the learned embeddings that you have in some of the let's say recommendation engines is very close to learning from data, is very close to machine learning, while I'm saying here it's data mining. So there's definitely an overlap of machine learning, data mining, and even for statistics which are needed in movie analysis. But we will also look a little bit when we look at what genres and so on we use, what are the voting disciplines of people voting popular movies. So basically you see, and hopefully in this lecture you'll understand that data science, what we do in the clouds and using computing, is really overlapping with different many facets of these established, let's say, general practices. But when you have a real life problem outside in the field, chances are that you have to combine them very much. Also here still the idea data needs to exist, right? And we think there's no exact mathematical formula that can now describe how you would vote basically a movie. But of course you can think about that here we will think about something that there's a pattern, right? You might be similar to a person, and that similarity is an important factor that we will also analyze now when we look closer on the recommendation engine. So there seems to be a pattern and there's data. So let's look at it more deeply. Hence, there are also many other algorithms I wanted to explain just briefly. You see here the key mains clustering is also very nicely supported with implementations in cloud environments. For instance, again, in the MLlib from Apache Spark, for instance, you can use that quite nicely. There are others which are also using collaborative filtering. I'll come to this in a moment. And here you see how k-means work. You basically have an unsupervised learning scenario. You don't know to which group these points belong, but the k-means is able to assign basically groups to these different data items based on similarity measures. You see here a little bit the Euclidean distance, finding the sweet spot in the middle of a cluster, as it is called. Hence, we call that clustering, right? Here you see 4 clusters. The tragic story of this k-means is, however, you have to pick the number of clusters beforehand. And there are others like HP DBScan, DBScan, and so on that don't need this information beforehand and will find automatically the number of clusters. Of course, they have other problems like the type problem they don't find and so on. However, the case is made. There are different clustering algorithms in machine learning, in data mining, and we will focus today with the collaborative filtering, and there are different collaborative collabs here available. So general idea is basically what you see here. You have different customers, of course, and you have different movies. So I think that's sort of obvious. Those that look Netflix and the Netflix movies, for example, and you will match them and then give certain ratings, right? You as a customer cannot just do maybe thumbs up and thumbs down, but also maybe rate them highly, rate them low, and so on. Hence, you can come quickly to an idea that for each of the movies, you can then, if you transform that a little bit into the idea that you have each of the different movies here, you have different users, and you can basically then predict and think about strategies. And this is where collaborative filtering comes in. There are different recommendation systems, as we will talk about. But here we talk about, are there similar personalities maybe found? Is there a user that rates movies similar like I do? And then I would maybe have a high chance to recommend a movie that is actually, basically something I also may like. So you see some similarities here in basically user 4, user 5 rating highly, 101 rating highly, 104. So chances are they are maybe also similar in these, basically 102 or 105 when we recommend to user for these movies, right? So, and there are different ones we will explore also now in more detail. But let us come also to an idea what could be other forms of recommendation systems first, because this is a large topic. There's a content-based, product-based. This is something where you would say it's more like a genre, right? So where you say, these are always the cowboy, the Western movies. So someone has looked at this and, basically something where, you don't really need much machine learning. You rather can do also DB lookup and your database upload and just can recommend this and say, well, when you look 10 cowboy movies already, chances are that the next 10 in our database maybe also suit you. Hence, this is, let's say, not so elaborate in terms of computing power, not so elaborate in terms of machine learning. It's rather databases. So hence, we will focus here a little bit much more on collaborative filtering, also sometimes referred to as customer-based recommendation systems, where really the point is now the similar personality, right? Not only like we had in association rule mining, what are the products that often go together, the frequent item sets, but here are the frequent item sets that a similar personality like you have, basically rated movies will be getting recommendations for. So we talk about a much more, let's say, a specific and trimmed recommendation for particular users. Of course, this means we have to look into different users. We look into different movies again, find the similarity, learn the similarity. And this brings us to a techniques of using different matrices or matrices for it, bringing us quickly to a topic called matrix factorization, which is not obvious for you, but we will see how that materializes in a couple of examples really from movies and users. Hence, here we look at the similarity again. And the overall methodology is, of course, that we have data from existing shopping, behavior. So needless to say, we need data. And what we want to do and to achieve is, of course, to see what customers would maybe look in the future or like in the future. So we do this here for the movie rental a little bit, but you see here in the idea of this, element, is there two sports people. Chances are that they maybe like something like, when he likes pizza, both of them like pizza, they both like salad. So when one of them is like cola, he can also recommend this probably very much to this other sport guy because, these seem to have similar personalities. So in the end, this is now a trivial example, but now you can imagine by looking over maybe a pattern of 100 movies that both people have seen, we can understand much more a pattern than maybe in this trivial example here, right? Which could be more or less a coincidence that there's another cola on the table. But still, think about this always, that of course the examples we give would be a couple of movies, would be a couple of pizzas here and salads. But the real world out there is, of course, having then movie data, which is quite large. And I will also point you to some data set where you can experiment yourself if you like. So, however, there are different machine learning methods that really can tackle this problem. And these go back to even much more mathematical foundational elements, like matrix factorization is something which is not necessarily just machine learning, can be used for many other elements in mathematics as well. So in general, you would classify them in memory-based and model-based system. So let's look at this a little bit more. These are quite different approaches that basically you see here. The techniques on the memory-based approach have then some, let's say, similarity measures that you use, correlation measures, and they are basically very easy to create, and you can have some weighted average of ratings, so you can even explain the results a little bit. But when you do this memory-based approaches, you basically have to do this over the whole set of movies and whole set of persons. So in this regard, by not using not smart model-based approaches in a way, it is basically computationally not really doable anymore at some point in time. However, it's of course nice because it has better explainability. Then the model-based approach is using then machine learning to find really user ratings. So maybe in a way not doing a brute force with similarity measures, person by person, and so on, but rather try to find patterns in the overall way. And there's like singular value decomposition, matrix factorization techniques we will look at. The point is it performs automatically sort of a dimensionality reduction. So we can use that a lot to basically have us much more a feasible approach to computing. And that is something which is, of course, for us quite interesting to look at. So, however, the inference is then not so interesting because we say, well, this user has a 0.74. That's why he want to have that movie. Thank you very much. So that doesn't help me anything. So hence we have mathematical models, or let's say matrices we learned, or embeddings we learned, which, basically give a precise understanding of the person versus movies, perhaps, but it's not really insightful when you think about it, it's just numbers. And these are the drawbacks. Coming back to the challenges then, that you have basically then, and look here on the illustration again, how it works. We would say the assumption is that there would be some customer that basically would be a similar personality, would be rating elements similar like the other. So this is something what we know basically from retail, which our gut feeling already says that people just like books, and people just look at books, maybe like look Lord of the Rings or science fiction, quite the opposite. Still, there might be a pattern that you can find that these people still would recommend each other. So in the end, we will find their patterns. But when you do this, let's say, profoundly, and not in this toy examples that you see here now, right, with 4, let's say, different features for users where you can learn from here, you need basically billions of transactions to really work very well. Of course, we have some smaller ones from the movie ratings, but in practice, if you want to do this and go out in the field and implement this, be careful. You need also quite, lots of data. And we don't have that data necessarily. Hence, it already alludes to something I want to conclude on. We use cross-validation techniques. Again, today, you learned that already in practical lecture 7.1. If you don't swim in data, you will use, validation sets for model selection again in so-called n-folds or k-folds. We come to that at the end. But the benefit is really then, of course, that it really works. So you can really have new opportunities, cross-selling products, maybe at the cashier level directly in front. When you pay, you can still ask, are you not interested also to buy this? Because, majority of the customers that are very similar to you bought also this. And chances are that you really say, well, yes, I forgot that. Or basically, that's something I'm interested in. Hence, it really works in practice. And you see here a little bit how that works in terms of this model-based approaches that we pick on, which algorithms are there. They're all basically here in the area of matrix factorization based algorithms, and we will use the surprise library. Again, that's something that is not always installed. And you see there are also some others like fast AI with neural networks now, basically using also and entering the territory in this recommendation system domain. But we stick a little bit here to the surprise package also, which is, of course, then relevant for your assignment notebook. Then also I want to do some connection again with the CRISP DM. Every time you see a little bit the wording here, data understanding, data preparation, modeling, evaluation. We had this already before in some lectures, if you remember. So here it's the same way. We start a little bit now with the problem understanding again. We have basically a movie feedback matrix. You see that quite nicely here. So people have looked this, where, you know, Harry Potter, the different movies you have here. And they have, let's say, simply liked them or not liked them or not looked them, right? So there's something which we know, and this is basically then the feature and the idea that we have to start from. So the idea then, what this feedback encoding is essentially that we have, you know, an idea with these embeddings that you see here in the, let's say, 2D domain. You see here a 1D encoding is also possible, mapping this basically here to the different personalities with the movies. But the interesting thing is with these approaches we have in collaborative filter, we learn these embeddings here automatically, right? So this is quite nice in order to find out then really how we can, you know, rate others in the movie. And I think the next slide will give you an indication to this. When we have the embeddings approach, you see essentially with the 2D, this space here a little bit where people already can be considered similar because they basically both, as you see here in the matrix, liked, for instance, Harry Potter, so and so on. And the idea is now the preferences here needs to be something which we can, you know, basically not grasp if we have lots of these different, let's say, movies. It's a big space, so we need an abstract representation for these items and the users, right? And we try to measure the similarity somehow. And in this end, you basically would say, okay, maybe, let's say, one value would be not enough for this complexity, right? Because now we're not talking about 4 users or 4 movies or 5 movies here. We talk maybe 100 movies, and basically features of a person might be much more, as we know from ourselves, not just expressible in a single number. And you see that how this then materializes if you have this 2D embedding example, where you then, let's say, add more and more feature space, or basically the embedding space here, where you then can learn from. And then by learning these numbers automatically, you basically can come to a point by, you know, getting these 2 matrices learned. You basically can use them later to understand where there might be a similarity. So what would you recommend, let's say, as one of the next steps, basically? And you can really compute this here and would basically say, you know, Shrek would be something that basically these 2 persons liked and these 2 persons liked. So chances are that this person, based on the numbers you have learned, will also basically be interested maybe in this movie Shrek. So that is something which is now, of course, here a visible illustration how that roughly works. The key thing is that from all of these ratings that you have, this space, which is purely mathematical in a way, will be now learned. And you can already see with this different features, we not having a vector here, we having rather 2 matrices that needs to be learned, not only in 2D, we can also expand here, of course, and having more features. Hence, this comes to the so-called matrix factorization approach now. So it's a bold word, which is not necessarily very, let's say, very complicated, where you have essentially this interesting matrix now that we said. And because this is something what is given to us, right? When we put that in a mathematical expression, but we want to do the learning here, right? So in a way, we want to find out what these 2 matrices, if we do, let's say here, the dot product of these 2, for instance, would be, so basically using, you know, matrix U and matrix V, and then basically find out here what would be then the matrix that will basically be resulting, or basically will be in line with what we have also in the rating. Hence, we will turn these things, which are yes and no's, into more mathematical expressions, but still fit. So minus for something which is not there, plus values for something that is there. Needless to say, as we learn, this is approximately correct, right? As we learned before, machine learning means learning from data in a probabilistic sense. So approximately, we will learn this, but it already gives us a quite nice view how to do it. And of course, it's a kind of optimization problem then to enable this at the minimum of error in a way through all of these will be then, reproducing in a way with these two matrices, which start basically as 0, right? We have nothing, but we can learn them because we have the kind of matrix which is the results. And this is a common problem which you now called break it into different matrices to see how we arrive to this, let's say, big A matrix that you see here representing roughly this. And there are different ways how you do it with the observed only weighted matrix factorization, or you use the SVD. That's what we want to do. For SVD, to explain it in very detail, of course, this would take a whole complete university lecture usually, also with its all varieties and also using some examples. So I would refer a little bit to a machine learning course again, or to mathematical, let's say, foundations even here and there. And for this course, it's of course not necessarily that you understand the very deep details, right? Important is that the SVD is implemented in many of the algorithms packages that we have available. One of the very nice Google Colabs that basically was not anymore there now in 2024, unfortunately, to show you, is here this one. And I would, let's say, recommend you to also look at the 2022 course. It's a bit more elaborate in the recordings in YouTube I did with this nice, kind of notebook. Unfortunately, for some reason, Google stopped that. So it's deprecated, it's removed basically. So documentation is still there, but the Google Colab in some respect is not anymore there. So we have to switch to a new one, hence explaining this interesting sign here. But you can look the YouTube recording of 2022. This is also practical lecture 11.1. So hence this is a new one, but it's the same that you have in your assignment. There are a couple of notes here. In the add discussion area, I will give you a couple of updates, right? So this, when you basically use directly this link that I give you in the assignment, you basically cannot execute that. There's some smaller things that I have to correct. Hence, when I now execute this, and I will turn very quickly also now to the practical so that you see how it works in practice a little bit, also with data uploading and so on, which are common questions. But there are a couple of things really you have to do before. And one of them is to basically use this and copy it to your Google Drive, assuming that all students have a Google Drive folder, or at least someone in your group has one. That's the first step you should gonna do. You copy that to your own drive. You see that usually on the icon here, if that's the, let's say, Google Colab directly, or basically your own copy that you have in the drive, it will switch to the Google Drive icon here. And of course, you should maybe rename it to your group, whatever you want to like. And the assignment, of course, is important to upload then the Python notebook alongside your results. Also very important is that you should start executing the notebook from the top. You see this, we introduce here lots of packages. For instance, the surprise package I already was alluding to upstairs in the different slides. So, but this is important, and then you need to focus on two elements, movie data, a metadata section here that you want to explore a little bit for understanding the data, perform data exploration, visualization, inspection of the data. And then we want to do later here the hybrid recommender, the collaborator filtering. So that is an error. Sorry for that. I'd like to correct this here. Collaborator filtering is what we want to do today. And the necessary data will be also available in the Canvas area. And I show you here also how you upload it. So when you started, again, remember, I have done here, for instance, a copy, and I will switch now more to the practical so that you see also basically what's happening. And this is a good point, something I also didn't, talked about yet. So you see here the file section. When you're not connected to any runtime, you don't have files. Now we have a nice, let's say, environment again, a runtime available again, and it has a data files area here, which is important for you because we will upload certain data. When you do this yourself, and you see here the Google Drive link, you started to copy it to your drive, you will not have these data, right? Links, movies, etc. This is all what I uploaded, and I show you how. So let's start by executing from the top. So you see we import here several libraries. Not all of them are relevant only for the collaborative filtering, as you understood. I think by now that the script is larger, you can do many different things with it. There are different recommendation engine you can compare to. For your assignment, just the collaborative filtering is of relevance, right? And of course, a little bit the data inspection and so on, as I show you today. So we start here with a very important factor. We install the surprise package. Again, the surprise package, as also here in the slides, is then something where you can look up and see what it entails. But basically for us, that means it has some of these SVD, I was just alluding to, matrix factorization techniques implemented that we're going to use to understand movie ratings. Hence, let's go to the practicals. It will be, in your case, installing it, downloading it so that it is available. Sometimes you see here from the original author from Google Colab, there's a duplication that doesn't really hurt us, but also doesn't help us really very much here to do this. It's already up to date, given we have done it above. Now, here's the first time where you have to have some data, movie metadata from Hugging Face. So you see that here, and this is also provided on Canvas for you. On the slides, I've given you also a reference here how that works. You have the Hugging Face. When you want, you can also go there. Some of you maybe even know Hugging Face already. In machine learning, it is becoming much more popular. And you have this, but you have to upload that first to your own, let's say, instance. And that's only work if you have a running runtime, right? Like T4 here, for instance, where you have the movie's metadata. Then you can refer it and read it as a comma-separated value here. And on bad lines is one of these things which you have to change because in your script it will be a little bit differently called. It has something to do with different versions, but I will show you how to modify it in the add. Then we do some data uploading, but also some data inspection already. So we will see here, we have interesting movies here, Toy Story, Grumpy Old Man, etc. We see different IDs, IMDb, IDs where we maybe also get some interesting ratings from. Here are all the columns as an overview. They're very important for us. Maybe also the vote average, vote count, and so on these different movies. So the metadata is normally typically very important for the first steps to really do basically understand a little bit the data at hand. It is not the ratings itself, right? But to understand a bit the distribution of the data, to understand what the data is about. Often people start with metadata, analyzing it. We call it also data inspection and do some visualizations. Hence, let's switch back to the practicals so that we can also stay in time. We will have uploaded this here already, so hence we can also now use it here. You see it in practice how that works. There's much more. These are just, let's say, a couple of lines here, 5 rows that we have. Then the different columns I was alluding to is very important for us to understand there's certain votes, for instance, we're going to use maybe later, and etc. etc. So hence we have like around 24 different features, if you want, for these different metadata elements, and of course they can be inspected. And that's what we do in the first part, and that's where basically also your assignment should be, like talking a little bit what you see here, what we do here. And always just 1 line or 2 line is enough, right? For these small cells especially. Here we see a little bit from the graph where is basically missing in our data some, basically elements, what we do there. You see a little bit again the 24 features here. So what does it tell us? Then we basically have reading the movie from the movie CSV. Here you have different choices. For the assignment, what we do here is we use a group lens data set in the small version, right? The ML latest small. that is available on the Movie Lens latest data sets. It's already uploaded also in your Canvas environment, so you can use it, and you have to upload it the same way as you would do it with the Hugging Face metadata, right? Important, there are many movies CSVs around, so it's good that you stick to this particular one. For some of you that are interested, there's also a bigger version. You see 1 megabyte versus 335 megabytes. So I encourage some of you to do this. It is not directly part of your assignment, but could also increase your grade for the assignment. So for those of you that have a little bit more time, maybe go ahead also to basically try it out, what happens if you use, 335 megabytes and see what happens. Coming back to the practicals, I think it's sort of obvious what we do. We go cell by cell. Now we have this read of the movies. We have, again, a title, the movie ID, and some genres, which is now important for us. So basically, we can classify them a little bit to the genre, what is also maybe interesting for us from the perspective of understanding the data. So looking at basically checking if there are any, let's say, bad values is also part of data inspection, data exploration, and so on. Then we're creating a plot for genre distribution. So that we see the most seem to be drama movies, and then different war movies and classifications are lower, children movies are lower. So the amount of movies here is quite much into comedy, thriller, drama. Here's an error, I think, in this script. Don't worry about this, but still we want to understand now this in the light of what are the ratings, right? So basically we have this vote average in the metadata. So we want to understand what would be the vote average in terms of the number of all the different votes we have. And you see that the most people look, basically around and would say it voted in the area of 5, 6, 7, or basically something like this. Hence, now we want to paint that both. We want to basically look at this and say, what about popularity of movies? So more on the level of 5, 7, and so on. And how many movies have been counted? So how many people have been watched? And you see that this is a little bit on the vote average now. It's a consistent, as we said, that basically those that are, let's say, more the popular movies seem to be often more recommended and also, of course, more looked at, which falls back to this histogram here that you see on the top. And these are insights which shows you a little bit more how the data works, which is incredibly important. So next is then use the links CSV, also coming back to my slide set just for you. And of course, in the assignment, you spend a bit more time, you will understand hopefully much more into detail. Basically there is the idea now of having also in this package that you download here, the links. I already put that on Canvas for you to understand a bit more, and then start also a bit with the preparation of the data set. Also here, just put some smaller explanations for these small cells. You see suddenly we have this IMDb ID there, movie IDs there. That is all helping us now to form, let's say, and prepare the data. For instance, we have lots of data where we want to know the name, and we also want to do this for the small data set. So hence we prepare from the metadata information now here, everything for the small data set, and keep only those which are basically in this movie data set in the small variant, right? If you use a large variant, be careful here, right? To not do this. And then you basically can plot another way just to check again, are there any null values basically when we have done this, right? And in this sense, we have something which is consistent, and in this sense, we can move ahead. So this is also all in the moment, I think, here for the assignment that you need to do in data understanding and data preparation. So then you can hop, if you want, from that directly to the collaborative filtering area, right, which is a bit lower here in the overall structure, which you come back to when you come to the table of contents here. You said, basically, as we said, also we established what collaborative filtering is at the top. You see we're using surprise library with singular value decomposition techniques to do the recommendations. So here we start now reading the ratings in. The ratings, again, no surprise, come out of the and I also put that in for you here. The ratings are also part of this ML small package, so already uploaded for you in Canvas, but you, the same story as the others, have to upload it yourself in your environment. And now we can connect nicely to what we learned before in different lectures. Although it was with deep learning, now we do similar things, right? We have the ratings learned. We see ratings are now existing as 2 movie IDs. That is important. The message is just telling us that the GPUs that we have here in the runtime is not really occupied, so we don't learn yet very much. Hence, let's getting to learn it. We learned about model selection techniques, validation, right? And we learned also the ratings might be not enough, like in the billions of transactions. So let's use K-fold or N-fold validation techniques that I also was explaining a little bit in practical lecture 7.1. And I hope you don't have forgotten that, because that's what you do when you don't swim in data like here. Of course, we have the larger data set available if you want, but this shows you nicely how this is done usually in practice. And then we see here the SVD is really one algorithm we can use from the surprise package to then perform a model on which we do then the cross-validation techniques. Now the CPU and the GPU is really used here, and really, you know, computing more this matrix factorization. And we got different folds here, and the idea on the different splits where we're going for with the cross-validation 5 is something which is in the area of saying it's quite a nice, let's say, RMSE in the end. So I think that's here for the demonstration quite okay to use it for then the training process, right? So explain that a little bit, how that is basically now coming to this with the SVD technique and cross-validation. But you will also remember that this is not the end of the story doing cross-validation. Then the real training and inference begins, where we basically had this in practical lecture 7.1. Again, we could have many hypotheses. So cross-validation was basically in this process here of validation to find, let's say, the right model with the right parameters on which we want to train then completely. And that is basically what we learned a little bit with the fold here. Now we throw everything back in the pot as it is shown in the, let's say, here in the script. We have the train set on which we now train with the whole data again, right? So we swallow a little bit of positive bias that we got through the cross-validation technique. We're using data already, but of course this has been using then the folding technique, and the bias is relatively small. And then in the end, we have here also the prediction that we can now do with different movies, and actually can also combine this then, of course, for the user ID, for which user you would basically then provide what, then, we would expect for getting, let's say, as an estimate in order to get basically a recommendation. So this is part of your assignment, and you can play around a little bit with these movies and see that it goes up and down in the estimate of what you basically would say. And that's all really what I wanted to leave you on the table from the demonstration. Of course, when you do it yourself, then of course you have the chance to do this a bit more slower, and also can play around a little bit, play with the graphs that we have seen, understanding the data more, and then write this all up in assignment 3 and load it up. A small thanks to my team that also helped here. You remember also Heman in the first part helped me quite much with installing the kernel in the JC cloud. I'm grateful to my team. And I would say we see you again in lecture 12 next time. Thank you very much.